Hello my dear friends, I welcome back you to my YouTube channel Beginners Chemistry, where you can learn the chemistry in the easy manner. Okay, in our continuation lecture of solutions, we have completed the introduction of the solution, and then after we have seen the concentration terms, and in that concentration terms we have seen the interconversion between the molarity and the molality, and normality and the molarity, and the molality and the mole fraction. Clear? Now this we have seen, and I was given the some questions also in the previous lecture, and what are the answers that question solution we are going to do in this, and followed by we will start our lecture. Okay, now let's start our lecture. Now we'll start with the last lecture's question solution. In the last lecture, what I was given, 36 point HCl as density equal to 1.20 gram per ml, molarity and molality respectively is asking. What is asking? Molarity and molality. Okay, first what we do, according to the given data, we'll find the molarity. According to the given data, we'll find the molarity. After that, we are having the one beautiful relation between the molarity and the molality, right? From there, easily we will get the molality. So first, here they have given the 36.5 percentage of HCl. 36.5 percentage of the HCl is nothing but weight by weight percentage. Clear? 36.5 of HCl into, before, if you want, I will write the formula. What is the formula we are having? Weight by weight percentage into density into 10 by which one? Molecular weight. Molarity is equal to, this is 36.5 into 1.20 into 10 by HCl molecular weight will be 36.5. 36.5. Here the 36.5, here the 36.5 will be get cancelled. How? Chlorine is a 35.5 and hydrogen is 1. So here it will be get cancelled. And what the molarity, what you will get? The molarity you will get the, how much? 120 by 100 into 10. Clear? That you will get the 12 is a molarity. 12 is a molarity you will get. Clear? Next, he is asking the molality, right? He is asking the molality. For that one beautiful relation we are having, right? What is the beautiful relation we are having? Molality is equal to molarity into 1000 by density into 1000 minus molarity into molecular weight of solute. Molecular weight of solute. Molarity, how much we got? 12, right? 12 into 1000 by density, how much they have given? 1.20. 1.20 into 1000 minus molarity 12 into molecular weight of the solute. Molecular weight of the solute is how much? 36.5. If you solve, you will get approx somewhat 15.7. Somewhat 15.7 you will get. So the option number 4 is correct for the given question in the last lecture. Okay, now we'll move for this another one important and the beautiful question they are asking, that is calculate the normality and the molarity of the following. For this data, what is asking? For this data is asking the normality as well as the molarity. But first with the given data we'll solve with the normality. First we'll solve the normality, then after we'll go with the molarity, or else first we'll solve the molarity, we'll go with the normality. First what I will do, I will go with the normality of this A. Normality of this A. What is the normality formula? Normality is equal to equivalence. Normality is equal to equivalence by volume in ml into 1000, right? But what is the equivalence formula? Weight by equivalent weight, right? So N is equal to weight of solute by equivalence weight into 1000 by V in ml. So what is the equivalent weight of the calcium hydroxide? Equivalent weight of the calcium hydroxide, molecular weight by its n factor, right? Yesterday itself I said you calcium, what in the last lecture itself I said you calcium hydroxide, its n factor is 2 because here the replaceable OH minuses are 2. So its molecular weight will be how much? 74 by 2. 74 by 2. If you whatever the data they have given, 0.74 by 74 by 2 into 1000 by 5. If you do approx the normality, you will get 4. Approx the normality, you will get the 4. Clear? In factor we got the 4 for this one. In factor how much we got? 4. Now for this one we have to find the molarity. How to find the molarity? Yesterday we have derived the one formula. Normality is equal to molarity into n factor. Molarity into n factor. So if you bring the n factor to the left hand side, normality is 4. N factor for the calcium hydroxide is 2. So the molarity of this one will be the 2. Molarity will be 2 and the normality will be 4. Clear? Now we'll go for the B. We'll go for the B. For the B, what they are asking? 3.65 gram in 3.65 gram in 200 ml. 3.65 gram in the 200 ml of the solution. 3.65 gram of which one? HCl is asking. HCl in 200 ml is asking. Now equivalence of the or equivalent weight of the HCl is 36.5 by 1. 36.5 by 1. So normality will be equal to 3.65 because this is equivalent. This given weight, right, by equivalent weight. Equivalent weight is 36.5 into 1000 by 200. If you do approx, you will get the normality 0.5. So normality 0.5 and molarity into n factor. If you bring the n factor for the HCl is 1. Yesterday I explained very clearly. Molarity will be equal to 0.5. Normality will be 0.5 and the molarity will be 0.5. Clear? And the next data they have given 1 by 10 mole of H2SO4 in 500 ml of solution. Okay? What is asking? What is asking? 1 by 10 mole of H2SO4 in 500 ml of solution. Here normality we have to find. How to find the normality? Yesterday before when I was deriving the normality questions, I was explained one beautiful formula. What is that? Normality, not normality, we'll go with the gram equivalence or equivalence. Equivalence is equal to number of moles into n factor. This is a formula I was derived for you yesterday. The given number of moles will be 1 by 10 and H2SO4 n factor is 2. N factor is 2. How much you will get here? Now by this you got the what? Gram equivalence or equivalence you got. So 2 by 10 into 1000 by 500 ml. Is it clear? Okay, sir, we did not understand. Can you explain elaborately? Okay, now I will explain elaborately. Now you see, normality is equal to number of or gram equivalents or equivalents by volume in ml into 1000, right? Into 1000. Here gram equivalents, how much you got? 2 by 10. 2 by 10. Volume how much again? 500 into 100. That only I wrote. 2 by 10. 1000 by 500. How much you will get approx? This you will get the 0.2. Then normality is equal to molarity into n factor, right? Molarity into n factor. Normality is 0.2 and n factor for the H2SO4 is 2. Then the molarity will be how much you will get? Sorry, here you will get 0.4. 0.4 by 2 if you do, molarity will get 0.2. Clear? I hope it is clear. Now, next one another type of the question also I was given. What is the another type of the question I was given? This is 4 gram of the NaOH contained in the 1 deciliter of aqueous solution. 1 deciliter of the aqueous solution. In the 1 deciliter of the aqueous solution, calculate the following in the solution they have given. Following solution. What is asking? Mole fraction of the NaOH, molarity of the NaOH, and the molality of the NaOH is asking. Now we will see how to solve this question. First, before going to solve this question, first you solve the for the given data molarity. First, for the given data, you calculate the molarity. How to calculate the molarity? Number of moles. Number of moles will be the weight of solute in gram by molecular weight into 1000 by V in ml. V in ml. Here they have given the 1 deciliter. 1 deciliter. 1 deciliter will be equal to 100 ml. 1 deciliter will be equal to 100 ml. So weight they have given for NaOH. Sodium is 23 and oxygen is 16 and 1. 23 plus 17. 23 plus 17 how much? 40 into 1000 by 100. If you solve, how much you will get? Here 0 0 will get cancelled and 4 4 will be get cancelled and it will get the molarity will be 1. Molarity will be 1 you will get. Clear? Molarity you got. After getting the molarity, he is asking molality, right? He is asking molality. Molality is equal to molarity into 1000. Molarity into 1000. Density also he has given in the question. How much they have given density? 1.30. 1038. Density they have given 1038. So 1.038 into 1000 minus molarity is how much? Molarity into molecular weight of solute, right? Molecular weight of solute is how much? Molecular weight of the solute is NaOH, right? Molecular weight of the solute. Done. Molecular weight of solute. Molarity is 1, right? So 1000 by 1.308 into 1000 minus molecular weight of the solute is 40. If you solve approx the molality you will get 1.002. 1.002 something you will get. Okay. Next, now we are going to see mole fraction. Mole fraction is equal to, what is the mole fraction? Number of moles of solute by solvent plus solute, right? Weight of the solute they have given. Molecular weight of the solute they have given. Clear? But weight of the solvent they have given. Weight of the solvent they have not given. How to identify the weight of the solvent? But luckily they have given the density. You can see density they have given. How much they have given the density? Density is equal to 1.038 they have given. Done. Now, if they have given the density, how to identify we can identify the weight of the solvent. How? Density they have given, right? Density 1.308. Density formula, weight of the solution by volume of the solution. Volume of the solution, how much they have given? 1 deciliter, right? 1 deciliter is nothing but 100. If you cross multiply, what you will get? Weight of the solution you will get. Weight of the solution, how much? 1.308 into 100. 1.308 into the 100 is a 1.038 into 100. You will give 103.8. 103.8 you will get. Clear? From the weight of the solution, we are having the one beautiful formula, right? Weight of solute plus weight of solvent. Weight of solvent. Clear? Weight of the solution is 103.8. Weight of the solute, how much again? 4. Then weight of the solvent you will get from here. Weight of the solvent you will get from here. Weight of the solvent, how much you will get? Weight of the solvent you will get approx something around 99.8 you will get. This is weight of the solvent. This is the weight of the solvent we got. After getting the weight of the solvent, now what we are having? Mole fraction chi b is equal to weight of solute. Weight of solute how much again? 4. Molecular weight of the solute is 40. And weight of the solvent how much we got? 99.8 we got. And molecular weight of the solvent is 18 plus 4 by 40. 4 by 40. If you solve, you will get the mole fraction of the NaOH. Mole fraction of the NaOH. Approx you will get 0.0177. 0.0177 you will get. Okay. Now these are the questions that we have given in the last class and that we have studied in the that I was given in the last class, and those are the solutions for it. Okay. Now next we are going to study what we are going to study, that is solubility of the solids in the liquid. How the solids are soluble in the liquids. Before going to this one, now I will give you one definition of this one: solubility of solids in liquids. Clear? That one, maximum amount of solid dissolved in 100 grams of liquid to form a saturated solution. Clear? Solubility of the solid. What is the solubility of the solid in the liquid? The definition: maximum amount of the solid that dissolved in the 100 gram of, here I was taking 100 gram of the water. In this 100 gram of the water, that maximum amount of the solute when I was added, that it will become the saturated solution. What is the meaning of the saturated? Already I explained you. What is the saturated? Dissolution. Solute plus solvent gives rise to solution, that is dissolution. And that dissolution solution, again it is converting into solute plus solvent, is called as a crystallization. So rate of dissolution and the rate of crystallization both has become equal, and that solution we call it as a saturated solution. I was explained very clearly. Clear? Now here this is, now if I ask density, this you have to remember, Amma, this is very very important. Density of H2O is 1 gram per ml. 1 gram per ml. Clear? This you have to remember. Then now what are the factors that are affecting? What are the factors that are affecting which one? Solubility of solids in the liquid. Solubility of the solids in the liquid. What are the factors that are explaining? Now we'll see. First factors that is explaining. First factors affecting solubility of solids in liquids. Solubility of solids in liquids. Clear? The first one is nature of solute and solvent. Nature of solute and the solvent. What is the nature of the solute and the solvent? Here, what is the meaning of the nature of the solute and the solvent? First thing here you have to remember is polar solute plus polar solvent will give you the solution. Means more solubility will be there. Polar solute and the polar solvent, and non-polar solute plus non-polar solvent. Here also will be more solubility will be there. Means that I can say like dissolve, and unlike dissolve, unlike dissolve, un, unlike dissolve or non-like or unlike dissolve, unlike. Clear? Here polar solute plus polar solvent giving the high solubility solution, or more or less more fastly the soluble will be appeared. Clear? And the unlike dissolve, unlike, or non-polar solvent dissolve, non-polar. Sir, can you explain very clearly for us, sir? Okay, I will explain. Now listen. Here what I was taking the general example for you, very general example for you. NaCl solid, NaCl solid I was taken. This NaCl solid, first I was giving the heat, I was giving the heat for this one. When I was giving that heat, that I was saying that one, it is a lattice energy. That energy, whatever the energy I was giving to the NaCl solid to make into its consecutive ions, make into two consecutive ions. Make into its consecutive ions means Na plus gas and Cl minus gas, Cl minus gas. Clear? Here whatever the energy it is coming, that is lattice energy. What we are giving the energy, right? We are giving the energy to convert this NaCl solid into its consecutive ions. So here the lattice energy is positive. Here the lattice energy is positive. Done. Now here this, after converting into the Na gas and the Cl minus gas, this Na gas, what it will do? It will be occupied with the H2O, occupied with the H2O, because this is a charged species and this is a polar and this is a polar compound. How the polar compound? Oxygen, this is the oxygen, sir, this is the H2O, right? H2O, it is having the partial negative here, it is partial positive here, here it is a partial positive. Clear? This Na plus ion, this Na plus ion, it will be attracted with the H2O molecule in this manner, attracted with the H2O molecule due to the, clear? Now you can see here it has been attracted with the water molecule, right? Oxygen due to the partial negative charge and sodium due to the partial positive charge, oxygen due to the partial negative charge. Clear? Oxygen here the partial negative charge. Now oxygen here the partial negative charge. Clear? Now you see this sodium has been surrounded with the water molecule. This sodium has been surrounded with the water molecule. When this sodium has been surrounded with the water molecule, now you see this negative charge and the positive charge will form a bond, or it is attracting. When this sodium has been surrounded with the H2O, when this sodium has been surrounded with the H2O, from here the energy will be released. When these bond, when these are attracting, this oxygen OH minus charge and the sodium plus charge, when they are attracting, energy will be released, that released energy we call it as a hydration energy. This released energy we call it as a hydration energy. Clear? Which energy we are saying that is released energy, we call it as a hydration energy. Okay, whatever releasing, right? Energy is releasing. Here we are giving the energy, supplying the energy means lattice energy is positive. That energy we call it as a lattice energy. Lattice energy is positive. Clear? Now here hydration energy means energy is releasing. Hydration energy is negative, right? Energy is releasing. If suppose compared to the lattice energy, if hydration energy is high, then that solid will be soluble in the solution, or that solid will be soluble in the solvent. Clear? Now you see this, all the surrounded, this Na plus ion has been surrounded with the H2O, right? And it has become the Na plus aqueous, and this has become the Cl minus aqueous. Clear? Cl minus aqueous. This Cl minus also will be attracted with the H2O molecules. How it has attracted? Now you see here. Now here what it has happened? Now you see here. Just remove it here. Now you see here, this is H2O, right? You can see this is H2O, this is oxygen, and these are hydrogens. Hydrogens are attracted with the chlorine. Now you can see here the oxygen is attracted with the Na plus ion. Now due to that, you can see, I hope it is visible for you, but wait, I will make it somewhat. Slightly negative, what is saying, slightly negative, you can see slightly negative oxygens are attracted to the sodium cation, and slightly positive hydrogen are attracted to the chlorine ions. Now you see this hydrated cation means all the water molecule has been surrounded to this one. That's the reason this is hydrated. Clear? Now this we say it as a hydrated one. Now you see this is a hydrated chloride ion, because this has been surrounded with the H2O here. Due to that, energy released. Clear? What does it mean? Like dissolve like. Example. What is the example for this one? H2O solvent plus NaCl gives rise to the NaCl solution, right? NaCl solution. Or else sugar, H2O plus sugar, that also will give you the sugar solution. Clear? Now here you see what are the solvents that it is going to dissolve, the like dissolve like and the unlike. Or unlike means non-polar. Here polar solvents are, these are the polar solvent: H2O, methanol, ethanol, acetone, acetic acid, ammonia, what, acetonitrile. These are the polar solvents. Now non-polar solvents are pentane, hexane, cyclohexane, benzene, toluene, chloroform, and the diethyl ether. These are the non-polar solvents. Non-polar solvents will dissolve non-polar solutes. Polar solvents will dissolve the polar solutes. Clear? Now next we are going to see effect of temperature. Now what is the effect of the temperature that it is having for the what, solubility of the solute in the liquid, effect of temperature. What is the effect that we are having for the temperature? Now we'll see. First one, in the effect of the temperature, the substance okay, no, the substance whose solubility increases with the which one? Substance whose solubility increases with increasing temperature. So these are the some substance we are having. This substance solubility will be increased with the temperature. If we increase the temperature, this solubility also will be increased. Which one? Now you see. First example for this one, solute plus solvent, that it is converting into the solution. Here the condition delta H is negative. Sir, can you give the generalized example to make us to understand it very clearly? Example, I will take one cold coffee. This is one cold coffee. Let us assume this is one cold coffee. Okay, temperature is low. Okay, now I will take one hot coffee. This is one hot coffee. Coffee is hot, a tea is soft. Okay, done. Now here what I will do, here in this cold coffee I will add the sugar. In this I will add the sugar. Now in this I will add the sugar. In this I will add the sugar. Okay. In which case, or else in the generalized example also you can do it at your home. You take the normal very cold or less heated tea and very high heated tea, and the same amount of the sugar you take. Okay, same amount of the 1 tablespoon and 1 tablespoon, and if you add in the both, and you see after 5 minutes or after 10 minutes, you can see in which case the sugar has been dissolved. You can see most of the cases, you can see in this hot concentrated in the coffee case only, what it will happen, solubility of the solute will be dissolved, or that sugar will be very fastly, it will be dissolved. That only solute and the solvent, when you add the solute to the solvent by increasing the temperature, what happened, that solute, it will be converted into solution very fastly. Solute that will be converted into solution very fastly. That nothing but dissolution will be happen very fastly. Clear? Done? Examples, sir. Can you give me the examples for? Okay, I will give you that. Those are NaCl, comma, KCl, comma, NaNO3. Clear? NaNO3 and the KNO3. These are the some ionic compounds that are increased with the increasing temperature. This solubility also increase. Clear? Next, second, substance whose solubility will be, substance whose solubility decreases, with increasing temperature. With the increasing of the temperature, this substance or this solutes solubility will be decreased. Here the condition delta H will be the positive. Delta H will be the positive, means solute solid plus solvent, what happened, which has been converted into the solute, again it will be converted into the solvent, or solvent and the solute. Here those are the examples for this one, which upon increasing the temperature, the solute which has been soluble, again it will be, or solubility is less. Example is sodium carbonate and lithium carbonate and the cesium carbonate. Clear? These are the some example. Upon increasing the temperature, those solute solubility will be decrease. Clear? Next we are having the another type of the salt. This one we call it as a Glober salt. Clear? What is this? Sodium sulfate. Here what it will happen? Here upon increasing the temperature, there is no change in the solubility. Upon increasing the temperature, there is no change in the solubility. Here you can see how it is not having the solubility. There is no change in the solubility. First, when we are increasing the temperature up to 34 degrees or 32.8 degrees, this salt has been, solubility is increasing. You can see according to this graph, up to 32.8 means up to 32.7 degrees Celsius, solubility is high, right? But once this 32.8 degrees Celsius, when it has happened, what it has happened, its solubility is decreasing. Clear? This sodium sulfate, first by increasing the temperature, it is increasing, solubility is increasing. After that it is decreasing. There is no any change in the solubility. Okay, clear? Now this is example. Which one? Sodium sulfate is a example for it. Clear? Next, very most important topic that we are going to study, that is solubility of an gas in a liquid. General example I will give you for this one. Solubility of a gas in a liquid. Generally we used to drink our cool drinks, right? Thumbs up or something extra, something cool drinks we used to drink. In that cool drinks, if you open the Dakkan of it, what it will happen? The gas of that gas which has been compressed in that liquid, it will be come out, right? It will be come out. Clear? What is the meaning of that one? Gas is dissolved or gas has been soluble in the liquid, right? With the high pressure, So what is the definition of this one and what are the factors affecting this one we have to study. So now what is the definition of this one? Solubility of a gas in a liquid. Solubility of gas in liquid. Solubility of gas in liquid can be defined as volume of the gas in centimeter cube which will dissolve in 1 centimeter cube of liquid to form saturated solution at a particular temperature and pressure. At particular temperature and the pressure is known as this is a definition of the solubility of a gas in a liquid. Clear? At that particular temperature, how much gas has been dissolved in the 1 centimeter of the liquid to form a saturated solution is known as the solubility of the gas. Clear? In the questions, whenever if you want to see, I was taken the 1 ml of the liquid I was taken. In this 1 ml of the liquid I was taken. In this 1 ml of the liquid, some gas has been dissolved, right? Some gas has been dissolved in this liquid. So how much gas has been dissolved in this liquid you want to calculate. For that one, what you have to do? You have to take this gas volume condition. First, this gas, how much volume it has been dissolved in that 1 ml of the solution if you want to calculate. For 1 ml or any given ml of the solution if you want to calculate, first what you do, this gas you convert into STP. Convert this into the STP or NTP. Okay. What is the STP conditions? 1 atm and 273 Kelvin, right? 273 Kelvin. Sir, how we can find the volume of this gas has been dissolved in the liquid, sir? I will explain. Some data they have given. Let's suppose this one, pressure of this one they have given the 2 atm. Okay. Now volume they have given something 50 ml. Okay. Then temperature they have given something 300 Kelvin. Clear? This gas, if this data they have given, now you have to assume or you have to convert this into the STP condition. From there you can find out the volume. How? Now we are in the ideal gas equation. We are having this formula, right? P1 V1 by T1 is equal to P2 V2 by T2. P2 V2 by T2. P1 how much we are having? 250 and 300 is equal to P2 how much we are having? This is P2. This is T2. V2 we have to calculate. P2 is how much? 1. V2 is how much? We have to calculate. T2 is how much? 273. If you interchange, you will get the volume of the V2. Clear? From here, you have to calculate. Clear? Next, we are going to see what we are going to see. Factors affecting what? What are the factors that are affecting the solubility of the gas in the liquid? Solubility of the gas in the liquid. General examples only, amma. Well-known example for you only. These all are the well-known example for you only. Okay. Solubility of the gas in the liquid. First one, what we have to see, factors affecting solubility of gas in liquid. Factors affecting solubility of the gas in the liquid. First one, nature of the gas and solvent. Nature of the gas and the solvent. What is the nature of the gas and the solvent? Nature of gas and solvent. Nature of the gas and the solvent. What is the nature of the gas and the solvent? First thing, here we are going to see, here H2O I was taken. This is a H2O. In this H2O, if I was at O2, H2, N2, if I was, gases are there, these gases will not be soluble. These gases will not be soluble. Why? Because this is polar solvent. These are non-polar solutes, right? These are non-polar solutes. Clear? Non-polar solutes in the polar solvent, these are less soluble. Clear? These are less soluble. Now, which one will be more soluble? Which one will be more soluble? Clear? Which one will be the more soluble? Like polar gases, SO2 plus H2O. What it will convert? It will convert into the H2SO3. These are the some polar gases with the polar solvent. It will be more soluble. If you want to find the which gases will be soluble in the H2O liquid order, I will give you the one order. This, based on this order, you can identify solubility of gaseous order which are going to soluble in the H2O. First, hydrogen bonding gases. Which one will form the hydrogen bonding with the H2O? Those will be soluble in the H2O very fastly. Second one is the polar gases. And the last one is a non-polar gases. Just now I explained, right? Next one is a non-polar gases. Done? Clear? Now, next we are going to see effect of temperature. With the effect of temperature, how the solubility of the gas is affecting. Effect of temperature. This is generalized example only, and it is well known example for only. Now, here you listen. Here first we'll go to the shop. When we go to the shop, if you take any cool drink or any cool drink, we used to have, right, Thumbs Up or Sprite or 7-Up. Now, anything if you take, what it will happen? Gas will be compressed in it. If you open this Dakkan, what it will happen? The gas which is highly compressed in the liquid, whatever the gas has been soluble in this liquid, it will be evaporate out, right? Or it will be come out from it, right? Why it is coming out from it? Now you see, normally at low temperature, more the gas will be soluble in the liquid at low temperature. That's the reason only the cool drinks they will store in the which one? In the refrigerators. In the fridge, why they will keep these cool drinks? Because if you keep it that in this fridge at low temperature, more the gas will be soluble in the liquid. Once in the refrigerator, this cool drink, it is present in the refrigerator at, let's suppose, -2 degrees centigrade. From this -2 degrees centigrade, when that shopkeeper has given that cool drink to you, now you are in the room temperature, right? Normally room temperature, we will take it as a 25 degrees Celsius. Now, when this bottle has been came contact with the 25 degrees, means from -2 degrees to, it has increased its temperature to the 25 degrees. When the temperature has been increased, what happened? The solubility of the gas which is present in the liquid, it will be comes out. That's the reason when you open the Dakkan of that cooling the gas, it will be comes. Means solubility of the gas which has been soluble, it has been became less. Means upon increasing the temperature, solubility of the gas will be decreased. Solubility of the gas will be decreased. Clear? I hope you got it. What is the effect of temperature? What is the effect of the temperature? We can say solute, solid plus solvent, liquid, it is giving solution. When if the delta H is negative, means the delta H is negative, means from here at this condition temperature increases, solubility of gas, solubility of the gas decreases, solubility of the gas decreases. So that I can say you right, temperature is inversely proportional to the solubility of gas, solubility of gas, solubility of the gas. Clear? Now that's the reason only you see why the aquatic species, why the aquatic, sorry, why the aquatic species are more comfortable in cold water than the hot water. Clear? Why these aquatic species are more comfortable in the cold water than the hot water? Why? Because you see in the cold water, more the oxygen has been dissolved, Clear? Here more the oxygen has been dissolved in the cold water. That's the reason it is safe for the aquatic species which is living in the water. Now you see, if you increase the temperature, if the temperature has been increased, what happened? If the temperature increased, whatever the O2 gas has been dissolved in the H2O, whatever the O2 gas has been dissolved in the H2O, that what it will happen? That it will be evaporate out. If the whatever the dissolved oxygen, if it is evaporated from the water, now what happened to the aquatic species? Aquatic species will be die. Okay. Now this is first we have seen the first nature of the solute and the solvent, and the next we have seen the which one? With the effect of temperature. Clear? Now next we are going to deal with the effect of pressure. With the, if you increasing the pressure, what happened, or what is the relation between the solubility of the gas in the liquid with the relation with the pressure? Okay. Next, effect of pressure. Clear? Now you see what is the effect of the pressure? Mass of the gas dissolved, in liquid, is directly proportional to the pressure applied above the liquid. Clear? Mass of the gas dissolved in the liquid is directly proportional to the pressure applied on the liquid. Means what I am saying, if I was saying this 1 ml of the, some ml of the liquid I was taken, above this gas to be dissolved in this liquid, if this gas want to be dissolved in the liquid, what I have to do? I have to apply the high pressure here. I was to apply some high pressure. If I apply high pressure, whatever the gas it is there, that it will be soluble in the liquid. So can I say that mass of the gas is directly proportional to the pressure applied. Mass of the gas is directly proportional to the pressure applied. Clear? Now by that we will get a one beautiful relation. Clear? The mass of the gas, by removing the proportionality constant, one new constant will get, that is equal to Kp, that is equal to Kp. M is equal to Kp, right? They will ask you the graph. They will ask you the graph between M versus P. M versus P. How the graph you will get? You will get the graph straight line, right? This is y is equal to mx. Y is equal to mx. Sometimes they will ask you the graph between log m versus log p. Sometimes they will ask you the graph between log m versus log p. How to find the graph between the log m versus log p? Take the log on both sides. Take log base 10 on both sides. Already I explained you. Now whenever we are going to deal log values in the chemistry, we will deal with the base 10 only. We will deal with the base 10 only. Okay? Don't apply the whatever the log values you are applying in the maths and the physics. Okay? In our chemistry, if you are dealing with the log values, you have to consider its base is 10 only. Okay? Now here when you apply the log 10, here log m is equal to log kp. This one will become log m equal to log k plus log p, right? This is y is equal to mx c, right? Y is equal to mx c. Y is equal to mx plus c graph. Clear? The graph you will get in this manner. Done? Now, clear? Now, next we are going to study very important topic that is known as Henry's law. That is known as a Henry's law. What is the Henry's law? What is the effect of the pressure we have studied? And the Henry's law is almost equal. Now you see, what is the meaning of the Henry's law? Henry's law, what he has said, Henry's law he has stated, the solubility of the gas in a liquid, the solubility of the gas in a liquid is directly proportional to pressure of the gas above the liquid at a constant temperature. So can I say solubility of gas is directly proportional to the partial pressure of the gas. Sir, what is the solubility of the gas is directly proportional to the partial pressure of the gas, sir? Okay, now I will explain. Here we have taken one liquid. Okay, now this liquid, whatever the pressure it is exerting between, let's suppose this is A, this is B. Whatever the pressure we are getting in this container, that is due to the which one? A and B. Clear? These gases to be dissolved in this liquid. The solubility of the gas in the liquid. What it should be there? It should be directly proportional to the partial pressure of the gas. If the gas partial pressure is high, more it will be soluble. Clear? Is it clear? That's the reason in this Henry's law, what we will state, if the partial pressure of the gas is high, more it will be soluble, right? That's the reason solubility of the gas, what we used to take, solubility of the gas will be related with the, or will be equal to the mole fraction of the gas. Are equal to P gas. Clear? What we will do, if this gas partial pressure is high, more it will be soluble. So how it is having the more partial pressure means I will get to know by its mole fraction. I will get to know it by mole fraction. If the mole fraction of the gas is high, more it will be soluble. More it will be soluble. That it has been stated by the Henry's law. That it has been stated by the Henry's law. So by this, can I give a one relation? Mass is directly proportional to the pressure. Mass is directly proportional to the pressure. By removing the mass, by removing this proportionality constant, one new constant will get m is equal to Kp. M is equal to Kp. Now, this relation, this Henry's constant relation, I will relate with the, which one? Dalton's law. I will relate with the Dalton's law. Why I was relating with the Dalton's law? What is the Dalton's law? It has stated. Clear? Now, the partial pressure of the, total pressure of that solution will be equal to the partial pressure of the sum of the gases. What the Dalton's law has stated? Dalton's law has stated, whatever the gas or whatever the partial total pressure it is getting from this here, that it will be equal to the partial pressures of the sum of the gases. Here also, if the gas partial pressure is high, more it is soluble. So what I was doing, by relating Henry and Dalton's, by relating the Henry and the Dalton statement, solubility of gas equal to mole fraction of the gas will be equal to the P gas, means can I say mole fraction of the ith gas is equal to Kp. Mole fraction of the ith gas is equal to Kp. Can I say? Why? If the mass of the gas is I, means nothing but mass of the gas is I, more nothing but mole fraction is high. Clear? Now here we will get the different formulas, and whatever the constant we got it here, this constant we are saying it as a Henry's constant. Whatever the constant we got it here, we got the Henry's constant. But here Henry's constant formula will be different in the different books they have given. But whenever you are solving the questions of the Henry's constant, what you have to be very careful, because you have to be very careful with the units they have given. Depending upon the units they have given, based on that formula we have to use. Okay, we should not use the direct Henry's constant m is equal to k h into p or k p. We should not use that formula. What the formula we have to use, according to the units of the Henry's constant given in the question, according to that we have to use that formula. Okay, listen carefully. Now it may be somewhat confused for you, but I will make it clear everything for you. Now you just don't get confused. Now here what I was saying, solubility of the gas will be related to the mole fraction. Mole fraction is nothing but mass. Mass of the gas is equal to K into P. So ith gas will be equal to Henry's constant. I was give you some constant K, or I will give you somewhat K. Okay, some K into P. If two or more gases are present, we will define it as a partial pressure. If one gas is present, we will define it as a pressure. So solubility of the gas we are defining in the two terms. One is mass of the gas in liquid. Second, we are relating with the mole fraction. Of gas in liquid, mole fraction of the gas in the liquid. In these two terms we are relating. Mass of the gas formula, what we are giving? Mass of the gas is dissolved in the liquid is directly proportional is equal to K into P. Now K into P. This is Henry's constant KH. Now, what is the unit of this kh here? What is the unit of this kh here? Kh is equal to m by p. M by p. M is a gram and pressure is a atm. If suppose Henry's constant unit gram per atm if they have given, use this formula. Use this formula. Okay? If suppose, and the another formula we are having, in some books they have taken this 1 by k. 1 by k is a Henry's constant he has taken. This 1 by k is a Henry's constant he has taken. If the 1 by k is a Henry's constant, now the formula will be pressure of the gas. Clear? The pressure of the gas or partial pressure of the gas. If they are having 2. If the pressure of the gas, and this is a Henry's constant, into this is mass. Then what is the Henry's constant unit here? kh. kh is equal to p by m, right? P by m. And now the unit will be atm by gram. atm by gram. Clear? Now this is very, very important. Depending upon the Henry's constant unit, you have to solve the question. You should not use directly this formula and you should not use directly this formula. First in the question you see the Henry's constant unit, then use that formula. Use the formula. Then now comes to the mole fraction of the gas in the liquid. If the mole fraction of the gas in the liquid, if they have given mole fraction of gas in liquid. If the mole fraction of the gas in liquid, if they have given, how to solve? So mole fraction of the gas is equal to Henry's constant into pressure applied, right? Henry's constant into pressure applied. Clear? Now, here what is the kh unit? kh is equal to mole fraction by Pa. Mole fraction is a unitless. Mole fraction is a unitless. Yesterday I explained you what chi A plus chi B will be equal to 1. Why? Number of moles of solute by total NT plus which one? NB by NT. It will be get cancelled out and it will give you 1. So this is unitless. And the unit of this kh will be, what? atm inverse. atm inverse. And another formula also we are having. What is the another formula we are having? Pa is equal to 1 by kh chi A. This one they have taken it as a Henry's constant. If they have taken this as a Henry's constant, now the formula will be kh. Here the kh is equal to 1 by k, or else you can kh2 or you can take if you are getting confused. Okay, now the kh2 Henry's constant unit. Henry's constant unit is equal to how much it will become? Pressure of A and the chi A, right? The pressure of A is atm. If the Henry's constant unit, if they have given the atm, we have to use this formula. If the Henry's constant unit, if they have given the atm inverse, you have to use this formula. So you have to solve the given question or question according to the which one? According to the data. According to the data which they have, or according to the unit, you have to take the formula and you have to solve. We will do some questions also. I will explain very clearly. Don't worry. Okay. Now, what are the characteristics? Characteristics of Henry's constant. What are the characteristics of Henry's constant? Clear? Now, first Henry's constant characteristic is kh is directly proportional to the temperature. Okay. Second, kh depends on nature of gas. kh depend upon the nature of. Clear? Different gas will have the different kh value. This is very, very important. Oxygen, it is having the different kh value, and the N2 is having the which one? N2 is having the different kh value. Clear? Next, kh is inversely proportional to the solubility of the gas. This is also one important statement. This you have to remember. If the higher the kh value, lesser will be the solubility of the gas. Lesser will be the solubility of the gas. Clear? Next we'll see the some application or what are the applications of the Henry's constant that we are going to see. In the applications of the Henry's constant, where we used to see in the well-known example for this, right? These are the some cylinders we are seeing. Sir, what are these cylinders, sir? You may get a doubt. These cylinders are used by the scuba divers. Who are the scuba divers? Now we used to do the scuba diving, right? In these scuba divers, when they are doing the scuba dive, they used to have the cylinder, right? One scuba cylinder, one oxygen cylinder they used to. In that oxygen cylinder, what it will happen? If suppose 100% oxygen if it is present in that cylinder, what it will happen? If you go into the deep sea level, in the deep sea level, what it will happen? Higher pressure will be there. Higher the pressure will be there. Henry's constant or Henry's law is also same, right? Now, more the pressure you applied on the gas, higher will be soluble in the liquid. Same also, if this cylinder, if it is having the higher gas, air is nothing but gas only, right? Now, at the deep sea level, more the pressure will be applied on that, which one? That cylinder. If the more pressure is applied on that cylinder, more the gas will be come into our body. In our body, what it will having? Blood we are having, right? Blood is liquid. So, the more the gas will be enter into our liquid. Once if we commit from the deep sea level to the high sea or normal plane level, now at the plane level if you came, what it will happen? There deep sea level, higher pressure will be there. Now at the plane level, what it will happen? Pressure will be low. If the pressure decreases, what it will happen? Whatever the gas has been soluble in our body, that it will be evolved and it will give the bends and it will leads to death. So that's the reason to not to happen for that scuba divers. What they will do? They will fill these cylinders. They will fill these cylinders with the which one? Less quantity of the oxygen. How much quantity of the oxygen they will fill? Approx 32.1% of the oxygen they will fill, and 56.2% of the N2 they will fill, and 11.7 of the helium they will fill. Clear? This scuba diver, when they are taking the scuba cylinder, when they are going, what are the gases it will be there? Very less diluted, very less concentrated of the oxygen, and these two are the inert gases. Inert gases, what it will do? It will not allow the gases to be more soluble in our body. Clear? Done? Now, next application we used to see at the higher altitudes. At the higher altitudes, what it will happen? You can see at the higher altitudes, atmospheric air. Now, at the higher sea level, now sea level or higher altitudes. Sea level, what we are having? More the oxygen we are having. You see, this red dotted are the oxygen. Now, higher altitudes, what it will happen? Oxygen is less. Due to that, we used to get the what? Altitude sickness when we reach to the higher altitudes. At the higher altitude. Clear? These are the some applications of the Henry's law we are having. Okay. Now, and the questions based on the Henry's law that we are going to see in the next class. Okay. See you. Bye. And we'll see you in the next lecture.